So in today's class, we're going to talk about electrical currents. We're going to talk about Ohm's law, and we're going to talk about electrical energy and electrical power. So that's basically the content for today. I'm going to start with what I would call a microscopic picture or a microscopic viewpoint of electrical current, and a macroscopic picture, macroscopic viewpoint of electrical currents. So we get familiar with the idea of electrical currents, and we learn how to quantify electrical currents. Then I'll move on to Ohm's law, and with Ohm's law comes the concepts of resistance and also resistivity. So we'll learn Ohm's law, you've met it before probably, and we'll learn about resistance and resistivity. And then finally I'll say some words about electrical energy in electrical circuits, electrical power in electrical circuits, equations relating to electrical energy, electrical power in circuits. There's one point I wanted to make here. So in discussing conductors up to this point, we said that conductors in equilibrium throughout their volume have zero electrical field. Throughout their volume on the surface, they have constant electrical potential. In electrical circuits with wires and resistors and batteries, the conductors aren't in equilibrium. So in electrical circuits with batteries and wires and resistance, charge is moving. Current is flowing, and that's not equilibrium. So those rules about zero electrical field in a conductor, those rules about constant potential throughout a conductor, don't apply to electrical circuits. They're not in equilibrium. They are, though, in what we call steady state. That just means that the currents that are flowing in the circuits, the charges that are moving in the circuits are steady. They're constant. Okay, so the entire class is really about this sort of circuit, which I've pictured here. So there was a massive discovery in physics that goes back about 200 years. And it was a discovery by an Italian scientist, Volta, who discovered that with chemical reactions, using chemical reactions, you can create an electrical potential difference. You can make an electrical potential difference between two, what we call terminals. So one of them would have a more positive electrical potential, the other terminal, more negative electrical potential. That was a massive breakthrough in working with electricity. Up to that point, if you were a scientist up to that point and you wanted to work with electricity, the only way you can make your charge is by rubbing. And making your charge by rubbing things all the time gets very laborious. Volta came up with a way with making charge and allowing charge to flow that didn't involve rubbing. It used chemical reactions to push that charge, pull that charge around electrical circuits. So it's a huge breakthrough. So we're going to be talking about circuits that have a battery, thanks to Volta, and wires are connected to the two terminals of that battery. And then in general they're connected to some resistor. This is an example of a resistor, a lamp. And we're going to be exploring this circuit here. So the way that we normally draw this circuit in a circuit diagram, if you remember last class we learned to draw circuit diagrams involving capacitors. Here we're now adding circuits that involve resistors, is something like this. So this is a circuit diagram for that last picture. Upstairs here is the battery, which we met last class. Remember, we indicate that in a circuit diagram with these two parallel lines. One's long, one's short. One can be cut in half and made the plus sign. That's the positive terminal of the battery. One can't be cut in half, so it's the minus terminal of the battery. And then here's the new component. This is the resistor in the circuit. This, for example, is the lamp in the previous circuit. And so we're going to focus on this circuit. If you want to think about this circuit from the perspective of forces, the way I would think about it is that the battery is providing a kind of chemical push, a chemical force that is going to drive the charge, drive what we call the current, which is the flow of charge, around the circuit. So the battery is providing the push, the battery is providing the force, and as a result, there's movement of charge, there's a flow of charge around the circuit. So that's a force perspective where we think about forces, pushes, pulls, and we think about movement, motion. So that's one way of thinking about the circuit. If you think about the circuit that way, the resistor, what's the resistor? What's the lamp? What's that doing? It's kind of impeding the flow of the electrons around the circuit. It's impeding the current's flow around the circuit. So it's like a drag, an air resistance, or it's like a friction, a frictional resistance. It's impeding the movement, the motion. So that's what the resistor is doing. Another way you can think about electrical circuits is from the energy perspective. So if you think about this circuit from the energy perspective, then the battery, well, that's a source of electrical energy and electrical power. It's actually turning chemical energy, chemical power, into electrical energy, electrical power. So that's the source of energy for the circuit. The resistor is what dissipates, loses the energy in the circuit. Now, I should be careful there. It dissipates losing energy in the sense that the electrical energy that's flowing around the circuit gets turned into thermal energy. So if you touch a lamp, it's hot. If you touch a resistor, it's hot because you're turning the electrical energy that's flowing around the circuit into thermal energy, which is kinetic energy of all the atoms and molecules and electrons and protons that make up the material. The wires, from the energy perspective, are just like the transport system for the energy. So the wire from the battery to the resistor and then back to the battery again, that's just allowing the flow, the movement of energy around the circuit. So it's the transport of energy and power around the circuit. Okay, so let's now talk about our models of a key concept. Today's class is electrical current. Electrical current is flow of charge. So we want to define, quantify electrical current, the flow of charge. We give electrical current the symbol I, but let me start with a little analogy of electrical current. So this water current in this, let's imagine we went outside for a field trip and we go to the waterfall on campus. And we're staring at the waterfall on campus, and we're watching the flow of water over the waterfall on campus. That's a gravitational analogy to an electrical circuit. It's a gravitational analogy to an electrical current. Let me show you. So on this waterfall, right, upstairs here, the water has a higher gravitational potential energy by virtue of its height. Downstairs here, it has a lower gravitational potential energy by virtue of its lower height. So that there's a gravitational potential energy difference between the top of the waterfall and the bottom of the waterfall. And this flow of water is what we would call a water current. And we could quantify the flow of water, the water current, by defining the current to be the amount of material, the amount of mass of water that flows over the waterfall per unit of time. And so this would be a water current. It would measure the flow of water in kilograms per second over the waterfall and down the waterfall. That's how we would quantify water current. And so that's going to be an analogy to how we think about electrical currents. And actually, often in electrical circuits, you might want to think about this sort of water analogy, because it can give you some intuition that helps in understanding electrical circuits. Okay, so here is an electrical current that's flowing down a conducting wire. So in this picture here, just to go through it, in blue, this is some section of wire. So imagine some strip of copper wire or strip of aluminium wire. And I'm just picturing a little portion of it, a little section of it. Between the two ends of the wire is an electrical potential difference. Right between the two ends of the waterfall was a gravitational potential energy difference. Between the two ends of the wire is an electrical potential energy difference. It was because of the gravitational potential energy difference that the water flowed. It's because of the electrical potential difference that the electrical current will flow. So in my picture here, over here on the far left, this is a higher electrical potential. So I called it the positive end of the wire, positive terminal of the wire. Over here on the right, this is the at a lower electrical potential. This is what I call the negative end, the negative terminal of the wire. And now we're peering into the wire, and this wire happens to be filled with charges. It happens to be filled with charges that move, so what we call mobile charges. And these charges happen to be positive charges. So we're seeing a handful of these positive charges. Now, they're at higher electrical potential energy at this left-hand end of the wire. They would be at lower electrical potential energy at this end, the right-hand end of the wire. And so they're just rolling down the potential energy hill like the water rolled down the gravitational potential energy hill on the waterfall. So this is just an analogy of the waterfall, but not for gravity and mass. It's for electricity and charge. So the way that we quantify current, electrical current, which is flow of electrical charges, is imagine some sort of location along the length of the wire. So that's what this gray disk is meant to indicate. I'm going to look at this location. I'm going to imagine looking at this location. I'm just going to count the charges that go by. I'm going to count the number of coulombs that go by. And I'm going to count how many coulombs go by in a certain amount of time, in some elapsed time interval. And the electrical current is just the amount of charge that went by divided by the elapsed time. And so delta Q, that's the charge that went by. Delta T, that's the time interval. Delta Q over delta T is the electrical current. That's what we mean by the electrical current, and it's measured in coulombs per second, which is called amps. And so that's how we define electrical current. As you know, right, a wire, like a copper wire, or an aluminium wire, or a steel wire, inside that copper, aluminium, steel is actually not mobile positive charge carriers. Inside that wire is mobile negative charge carriers. Inside that wire is mobile electrons that are free to move. And so actually in wires, in circuits, it's typically negative charges, not positive charges, that are flowing, that are in motion. So here's the corresponding picture for negative charges moving through a wire. Over here on the far left, this is still a higher positive, this is still a higher electrical potential. So this is still the positive terminal. Over here on the right, this is still lower electrical potential. So this is still the negative terminal. So that's not changed on this picture. What's changed is when I peer into the wire and I look at the mobile charge carriers, now I see some electrons. So these electrons are what's in motion, as opposed to the positive charges in the last slide. And the other difference is that these are moving from the right to the left rather than left to the right. For the electrons, negative charges, moving from the right to the left in this picture, that's like them rolling downhill. See, they're repelled by the negative end of the wire. They're attracted to the positive end of the wire. They roll from lower electrical potential to higher electrical potential. So electrons over here on the right have higher potential energy, and they roll downhill to over here on the left, where they have lower electrical potential energy. But still, I could look at the wire, look at some location in the wire, count the amount of charge that's passing through that location, measure the time interval that that charge passed through that location, and quote the current, define a current as the amount of charge per unit of time. And again, I'm measuring in amps or coulombs per second. When we talk about here's an important point. When we talk about the direction of the current in an electrical circuit or in a wire, we define the direction of the current as the direction that positive charges would move. Although, this is the stupidity of it, in most cases it's negative charges that are moving. So if I was talking about the current direction in the previous slide and this slide, I would actually say it's left to right. It's in the direction that's opposite the motion of negative charge carriers. It's in the direction that's same as the motion of positive charge carriers. If you think about it, the motion of a positive charge carrier from the left to the right is actually just equivalent to the motion of a negative charge carrier from the right to the left. In both cases, if we move positive charge from the left to the right, we're making this more positive over here on the right and this more negative over here on the left. If we move negative charges the other way from the right to the left, again, we're making the right-hand side more positive because we're pulling away electrons. We're making the left-hand side more negative because we're putting electrons there. So although it's different charge carriers, plus or minus, although they move in different directions, they have the same effect. And they have the same direction. We define the same direction of the current. Okay, let's look at a microscopic model of electrons or other charge carriers moving through a wire. So in the microscopic model, I'm going to draw another analogy with the water flow. When water flows, say, along a river or along a stream or along a brook or whatever, it's flowing from higher gravitational potential energy to lower gravitational potential energy. Its flow is typically impeded, if you look at this stream, this flow of the water is impeded by the rocks and the pebbles and the stuff in the stream. Those rocks, those pebbles, those other things in the stream are a resistance, an impedance to the flow of the water down the river. And the same is true in an electrical circuit. So the charge that's moving through the wires of an electrical circuit, that flow of that charge is impeded or resisted not by tiny little pebbles or stones in the wires, obviously, but by the positive ions that the wire is made up of. And so collisions with those ions impedes the flow of the electrons down the wires. Let's take a look at that. Here's a microscopic picture of an electron flowing down a wire. So it's flowing from over here on the left to over here on the right in this particular picture. So this is the negative terminal that it's repelled from. This is the positive terminal it's being attracted to. And its motion, if you were to look microscopically at individual electrons, its motion is not simply streaming from the left to the right, but its motion is it'll move, it'll hit an ion, it'll bounce off the ion, it'll move a bit more, it'll hit an ion, bounce off the ion, and that repeats and repeats and repeats, and that's resistance. That's the impedance to the flow of the electrons along the length of the wire. So you see that happening here. The electron rolled downhill a bit and it struck a positive ion. bounced off. Struck another positive ion, bounced off that one. Struck another one, and then I got bored of putting the little red pluses in. But it keeps hitting these ions and bouncing around. And so as that electron, if you could really see that electron as it walks down the wire, it's not just some smooth, gradual walk, but there's a lot of random motion as it's bumping into, it's like walking down some really busy street, and you're bumping into everybody and dodging things, rather than smoothly walking down the street. So there's what we call random thermal motion. That's the kind of random movement of the electron as it bounces off things. And beneath that random thermal motion, there's what we call a drift motion. That's the gradual, consistent motion of the electron down the wire. So that's what, that drift motion is the motion associated with this travel from the left to the right. The random motion is just associated with its collisions with the ions and bouncing around. So, at the microscopic level, we said that the electrical current is associated with this drift motion of the electrons, individual electrons along the length of the wire. So you can actually write down an equation that relates the electrical current, remember that's the amount of charge per unit of time, to the motion of the individual electrons. So the electrical current is that quantity I. The individual motion, drift motion of the electrons is a quantity we call V subscript d. So it's drift velocity. So this slide summarizes the relationship between the macroscopic picture of the current flow, which is just in terms of coulombs per second, amps, and the microscopic picture of the mobile charges, which is described by their velocities, V subscript d. So the relationship, I've written it downstairs here at the bottom, this relationship between, think of this as the relationship between the current, macroscopic picture, and the velocity, the microscopic picture. This relationship involves, in addition to those two quantities, several other quantities that are basically characteristics of the wire. So let me just walk through them. Of the characteristics of the wire and the charge carriers in the wire. So firstly, one important characteristic is the amount of charge that an individual electron carries. So in this overhead, that's called E. A second important characteristic is the number of those electrons that are free to move per cubic meter. So it's kind of a number density of electrons. So that's in a number per cubic meter, so it's how many of these electrons. And then finally, the other number that's important in this relationship is the cross-section of the wire. So the number of square millimeters or square meters of the wire's cross-section. You can, if you think about a river, right? If you've got a very narrow river, a stream, right? It's harder for the electrons to flow down that, the water to flow down that narrow stream. If you've got a wide river, much more water can flow down that wide river. And this area of the wire, or the cable, is playing that role. Anyway, this is the relationship. So this is an equation we will use. This is the relationship between the current, the macroscopic picture of the current in the wire, and the motion of the individual electrons in the wire. This is their drift velocity. And it relates all these quantities that I've just listed here. If you want to check it, you could check the units. So if you check the units, N is per cubic meter. The electron charge is measured in coulombs. The speed is meters per second. The cross-sectional area is square meters. And if you look at these individual units, what you see, an interesting thing, right? The meters cancel out. There's meters cubed in the numerator and a meters cubed in the denominator. You're just left with coulombs per second, which is an amp. So this equation, although we didn't prove it, we can see that it's dimensionally correct. And it is relating the motion of individual electrons to the current that's flowing. Okay, let me show you a demonstration. I'll put the camera on. Oh, no. So if you wanted to imagine peering into a wire and seeing the electrons streaming down a wire when there's an electrical current, what you'd be seeing is a combination of a gradual drift motion of electrons along the length of the wire and this random motion associated with collisions of the electrons with the ions in the wire. And that's the kind of resistance, the impedance. So in this little demo, I never do that. It's like play socket with it. In this little demo, this bed of nails here, right? The nails represent the ions in a section of wire. And the ions in the section of wire, if you've got a bit of copper wire, you've got a bit of aluminium, steel wire, they're actually regular arrays of ions. So a steel wire, copper wire, aluminium wire is actually, at a more microscopic level, tiny little crystals of aluminium or steel or copper. And so it is regular arrays of aluminium, copper, steel ions. And then here's the electrons. And what we're going to see is that if I drop them in here, you see that there's some sort of combination of bouncing around, random motion, but also a drift motion. They all ended up, if I drop them in at the higher potential, gravitational potential, they all ended up at the lower gravitational potential. And so this is kind of an analogy of how electrons stream through a wire. And so that's how we kind of picture it. A combination of drift motion, that was the downwards motion, and random motion, that was the collisional motion. Another analogy is raindrops. So raindrops, well, they experience a gravitational force downwards, which you would think would just cause them to accelerate downwards, and it does to begin with. But they don't keep on accelerating. We're not hit by 500-mile-an-hour raindrops when we go out in the rain. Those raindrops are colliding with the atoms and molecules of the air. And so they experience a resistance too. So another analogy to electron flow through a wire is raindrops falling to the earth. They end up falling with a certain drift or terminal velocity because they're experiencing both a gravitational force and a resistance force. These balls falling down through the bed of nails were experiencing both a gravitational force downwards and a resistive force that was provided by the nails. And the same thing in a wire. There's an electrical force that's accelerating the electrons, but then there's kind of a resistance and impedance from the positive ions in the material. What's different, and what's quite interesting, here in the bed of nails or in raindrops, the drift velocities and the kind of random velocities, so it's similar scales in the bed of nails. For electrons in a wire, the drift velocities are actually much, much, much smaller. The random velocities are much, much larger. So if you were to look at electrons in a wire, moving along the wire, you basically see random motion, and only very gradually would you see them drift. And this question, this example problem, is for us to calculate that drift velocity. So let's see if we can do that. So we're told we've got a 200-kilometer long, 4-centimeter diameter copper high-voltage wire, and it's carrying 1,000 amps. So, this is typical of wires that are used in the electricity grid, that transport electricity across the country from power stations to homes. They're long wires. They're, large diameter wires. They're copper wires because that's a good conductor. And they carry large currents. So here's a kiloamp or 1,000 amps. What else to calculate for this 200-kilometer section of wire? How long it took an individual electron? Suppose we start watching one electron. How long is it going to take for it to get from one end of the wire to the other end of the wire? So we're just going to calculate that time. And we can calculate that time from the relationship between current, our macroscopic picture of charge flow, and drift velocity, and microscopic picture of charge flow, and that equation that we just met that relates those two. So let's go ahead and do that. Maybe I'll do this on the document camera. Look. Okay. Where did I put the pen? So I made a little sketch of the problem, which is what I've done here. Here's the section of wire. And there were a bunch of numbers that we were given in the problem. And I've listed those on my sketch. So the length of the wire is 2 times 10 to the 5 meters. So put it in SI units. The area of the wire. I was told the diameter of the wire, 4 centimeters. So the radius of the wire is 2 centimeters. So pi r squared gave me this area in square meters. It's 1.26 times 10 to the minus 3 square meters. The current in the wire is 1,000 amps. So we're also told that. And then finally, I was told that it was a copper wire. So that was a key statement, right? If you're told the type, the material of the wire, you can look up, it's in the textbook, for example, you can look up how many electrons there are, how many mobile electrons there are per cubic meter, which is a characteristic of the copper or the aluminum or the steel. And so I looked that up. Okay. So I want to figure the time that it's going to take one electron to travel the length of the wire. And I'm going to figure that the time that it takes one electron to travel the length of the wire, actually by firstly figuring out the drift velocity of that electron along the length of the wire, because that's why it's going to get from one end to the other end. So I'm going to find that drift velocity v subscript d. And then, once I've got the drift velocity, I'm going to think back to, those early, reminiscing back to early lectures of Physics 211, where we talked about velocity. So velocity is the distance you traveled divided by the time taken. We'll use that velocity relationship to find the time taken. So those are the two steps. Anyway, let's get going, otherwise I'm going to completely run out of time. This is the equation we're going to use to find the drift velocity. It's the relationship between current and drift velocity. And we're just going to turn it around and write it as a relationship for the drift velocity in terms of the known current. So it's going to be the current divided by NE over A. And if we look at that, I know the current, 1,000 amps. I know the number of electrons per cubic meter, 8.5 times 10 to the 28. I know the electronic charge. I actually didn't write it down here, but we all know that. It's 1.6 times 10 to the minus 19 coulombs. And finally, I know the cross-sectional area of the wire. It's roughly 10 to the minus 3 square meters. So I can fill in all those numbers. I'm not going to write them down, obviously, because we'll be here for 20 minutes. But if I fill them all in, I got the speed. And you might be surprised at the number that's going to come out. 5.8 times 10 to the minus 5 meters per second. That's a tiny number, right? You know, we can walk around at the scale of a meter per second. I don't really know what we walk around at, but something like that. These electrons, I thought they were going to be fast little guys. These electrons are really slow little guys in their drift motion. They're moving around at the scales of tens of microns per second along the length of the wire. So they're going very, very, very slowly. So that really is quite different from the bed of nails demonstration. In a wire, in a cable that's carrying a current, the drift motion is tiny, 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 especially compared to what is a very high-speed random motion of hitting the ions, colliding with ions. Okay, enough chat. Let's get on with solving the next bit, which is once we've got the drift velocity, from the definition of velocity, we can figure out the time taken to get along the wire. So this is just velocity equals distance traveled divided by time taken. I want the time taken, and I know now the drift velocity and the length of the wire. So I can rearrange it. The length of the wire is 2 times 10 to the 5 meters. The drift velocity was this 58 microns per second, so very, very slow. If I plug in those two numbers, I got 3.4 times 10 to the 9 seconds. That's a long time. It's hard to think about it. It's 110 years. It's a massively long time. If you think about it, you know, these wires haven't even been up for 100 years. So an electron that started at one end hasn't even got to the end of the wire, the 200-kilometer long wire yet. I mean, electrons are pouring out of one end of the wire. Electrons are going into the other end of the wire, so there is an electrical current, but it is a gradual creep. You thought, I don't know, snails were slow. Well, these electrons are really slow as they stroll down the wire from one end to the other end. So it's very, very, very slow drift. Okay. Let's talk about Ohm's law. So we think of Ohm as kind of the granddad of, did it just move to the right, the left? So what am I doing to do that? That's totally weird. Anyway. George Ohm. Ohm's law is named after George Ohm, and it was really the beginning of a theory of electrical circuits. Up until George Ohm, the idea of electrical circuits and how voltages and currents and things like that were related to one another was a complete mess, and he got it all organized. So Ohm's law, here's Ohm's law as an equation. We normally say V equals IR, because we don't want to keep saying the potential difference is equal to current times resistance, but it strictly is potential difference equals current times resistance, although we always say voltage equals current times resistance. What he discovered was the following. He discovered that the current that flows through a section of wire is in proportion to the voltage across that section of wire. So that if you increase the voltage, you'll get a larger current. If you decrease the voltage, you'll get a smaller current. So for wires like aluminum wires, copper wires, steel wires, or electrical resistors, or light, often fluorescent light lamps, incandescent lamps, the current that flows is in proportion to the voltage. And so he discovered that fact. I've written it down here. And the coefficient of proportionality is what we call the resistance R. And so this is Ohm's law. The greater the resistance, the lesser the current will be. So if you apply a voltage to something with high resistance and low resistance, you'll get a large current in the low resistance material or wire. You'll get a small current in the high resistance material or wire. So that's what this little relationship says here. I can show you this, what he discovered. So maybe I'll put the camera on this. I'm putting the camera on because my hunch is if I do this, it'll undo the movement of the slide. I don't know why I'm thinking that, but we'll see. Okay. So what you're seeing here is, I don't have a battery, but I have a power supply. So think of this as a big old battery. I have a resistor. This is a resistor. Looks like a strange resistor, but it is a resistor. It's a resistor where you can change the resistance. And then I've got a voltmeter. So this is measuring volts. The dial here is on V. And I've got a current meter. The dial here is on amps or milliamps. So right now what's happening is that I'm measuring in a circuit that's made up of basically the battery or power supply and the resistor, the variable resistor. I'm measuring simultaneously the voltage across the resistor, and I'm measuring the current through the resistor. So what you're seeing right now is 10 volts across the resistor, and you're seeing 200 milliamps. 200 milliamps current through the resistor. Now I can change the voltage. So let me go down to about 5 volts. When I went down to 5 volts, we saw just 100 milliamps of current. So I halved the voltage and I've halved the current. If I go down some more, I'm turning the wrong thing. If I go down to about 2 volts, no, I can't do it. Yeah, there's about 2 volts. I get about 50 milliamps of current. We've just seen Ohm's law. So if we had just done that, 150 years ago, we'd be famous. But we didn't. Ohm's first found it, but now we've discovered Ohm's law, that the current is proportional to the voltage. And the proportionality coefficient is simply the resistance of this resistor here, this variable resistor here. So this is simply Ohm's law. If I keep doing this, this is me demonstrating Ohm's law, the proportionality of these two things. Okay. Okay, but that didn't work. I mentioned resistance of a section of wire, or resistance of a resistor. The resistance of a section of wire, or the resistance of a resistor, depends both on the material of the wire or the resistor, and it also depends on the geometry of that material. And so this is sort of the accompanying equation with Ohm's law that tells you how that resistance in Ohm's law, how in V equals IR, the R depends on the material and it depends on the geometry. So in this overhead, I'm asking you to imagine some cylindrical section of wire again. Here it is. And we're going to imagine that section of wire has some length L, it has some cross-section A, and it has some what we call resistivity ρ. So the L and the A are reflections of the geometry of the wire. They're saying how long the wire is, how narrow or broad the cross-section of the wire is. And then the resistivity, that depends on the material of the wire. So you can look up resistivities of copper or aluminium or steel. Each of those has a characteristic resistivity. And then if you put the geometry and the material together, you can predict the resistance. So the resistance of this section of wire is the resistivity times the length of the wire divided by the area of the wire. That equation makes some sense if you think about it in the following ways. So the geometry of that equation makes some sense. So imagine you made the wire longer. Would you expect the resistance to go up? Or would you expect the resistance to go down? I'd expect the resistance to go up. If I make the wire longer, those electrons have got to go through, it's like they're walking through a forest of these ions. They've just got to whack their way through more forest, so there's going to be more resistance if I make the wire longer. If I make the area greater, what would I expect? How would I expect the resistance to change? If I make the area greater, I'd expect the resistance to go down. It's like turning a narrow country road into a freeway if you make the wire from thin to large. And so there's more room for the electrons to go down the freeway. And so if you increase the area, cross-section of the wire, the resistance goes down. So that equation, R equals rho times L over A, describes both those effects. Make a wire long, the resistance is going to go up because it's proportional to L. Make a wire have a greater cross-section, the resistance is going to go down because the area is in the denominator of the equation. Oh, a little quiz. Okay, so hopefully you can see this quiz. I've made the end date midnight, just because not everybody can. I myself managed to fall down in the parking lot, and at that time I thought maybe I'll send out an email to say it's a little bit icy out there. So I'm not empathetic or anything like that. It's just that I fell over, and therefore I felt I had to respond. Okay. So in this question, we're comparing 3 lengths of wire. They're all the same material, but they have different geometries. So there's one of them that is shorter, C, and there's one of them that has a smaller cross-section, it's B. And so we've got to order these 3 different cylinders or 3 different wires from the one that has the greatest resistance to the one that has the smallest resistance. So we want to think about that relationship between resistance and resistivity and the geometry of the wire. In particular, we want to focus on that dependence of resistance on the geometry of the wire. We said that if the wire is short, that's going to make the that's going to lower the resistance. If the wire is long, it's going to increase the resistance. And we said that if the area is large, then that's going to lower the resistance. If the area is small, that's going to increase the resistance. So the greatest resistance wire is going to be the one that has the combination of narrow cross-section and long length. It's this guy here. This is both, from the perspective of these three wires, a long wire, and it's a narrow wire. And so this one's going to have the greatest resistance. The one that's going to have, so B is, the one that's going to have the least resistance, well, that's the one that's going to be the shortest and the greatest cross-section. So the one that's got the combination of shortness and greatest cross-section is this one here. And so greatest resistance is B, intermediate resistance is A, and smallest resistance is C. And that's all about the geometry and how length and cross-section plays into the geometry and determines the resistance. Okay. Oh, I could demonstrate that for you, actually. Okay, so let me explain what I've got here. I, again, got a simple electrical circuit, basically involving a battery and a resistor, a wire that is a resistor. Here's my battery. It says power supply. And it's through two wires, a red and a black one here, delivering the current to two ends of a very thin, narrow wire. You can see it in the overhead here, in the camera here. So here's one end, one terminal from the basically the power supply, and here's the other terminal of the power supply, and they're connected along the length of this wire here. What you're seeing in this picture here is this is the voltage, sorry, this is the current along the wire. So this guy here is the current along the wire, and it's a little hard to read, but it's about 0.4. So let's call that 0.4 amps. If I was to reduce the length of the wire along which that current is flowing, it's measuring the resistance, sorry. It's measuring the resistance of the wire. This is 0.4 ohms. I managed to confuse it with every single quantity there is in an electrical circuit. First voltage, then current. It's actually resistance. This is the resistance. It's 0.4 ohms. If I shorten the length of the wire, this is 0.2 ohms, roughly. So I've halved the length of the wire, I got half the resistance. I can triple the length of the wire here, and now get about 0.6 ohms. So this is showing you that the resistance depends on the length of the wire. I've got different wires on this demonstration here. So this is actually a copper wire. And the one below it is the same diameter, but it's a steel wire. If I was to move the connections, to the other wire, now we see a different value for the resistance here. This is because these two wires have different resistivities. And so this little demonstration, I'm just showing you a fraction of it, shows you how the resistance depends on the length of the wire, and it also depends on the material from which the wire is made. Anyway. Last topic. So I want to say something about the flow of energy and power in an electrical circuit. We've been talking about the flow of charge and current in an electrical circuit. Let's move on to the flow of energy and power in an electrical circuit. So again, it's helpful to use the water analogy when we think about electrical energy, electrical power. So the water analogy for electrical energy, electrical power in a circuit, it looks something like this. Let's go back to, we'll go outside, go on the field trip, go to the waterfall on campus, and we're looking at the water flowing down the waterfall. It's flowing from greater gravitational potential energy to lower gravitational potential energy. So we're giving up, from an energy perspective, we're giving up gravitational potential energy. But, you know, we don't destroy it. It's turned into another form of energy. It's turned into thermal energy, which is energy associated with the motion of the, say, the electrons or the water molecules. And so if we were to picture the waterfall from an energy perspective, the waterfall is giving up gravitational potential energy and transforming it into thermal energy. If you measure, this has been done, if you measure the temperature of the water at the top of the waterfall and the bottom of the waterfall, there's a difference in the temperature at the top of the waterfall and the bottom of the waterfall. It's a little warmer at the bottom than it was at the top. That's because you've turned that gravitational potential energy. You couldn't destroy it. It's gone into thermal energy. So this is energy for a waterfall. Now let's look at the equivalent for an electrical circuit. So in the circuit, sorry about the slide walking away. I think he wants to get out the door. So here's a section of wire. Here's electrical potential difference across the length of the wire. That's causing current to flow along the wire. Here we're seeing some of these positive mobile charge carriers moving along the wire. And as they move from left to right, they are dissipating electrical energy. So there's a change in electrical potential energy as they kind of roll down the potential hill. And they're dissipating power, which is just the rate of dissipation of the electrical energy. And there's two equations that I want to introduce that describe that. They're down here. So as these charges move from left to right, from higher potential energy and higher potential to lower potential energy and potential, they release energy. They release electrical potential energy. And this is the equation that describes that. So this is the equation that quantifies how much energy gets released when charges flow in a circuit. The potential energy released is the product of the amount of charge you moved times the potential difference that it moved through. So if you move more, it says if you move more charge, then you're going to release more energy, electrical energy. It also says if you move the charge through a greater potential, you'll release more energy. Think about the waterfall. If you had more mass of water rolling over the waterfall, you'd release more gravitational potential energy, obviously. If you had a greater height waterfall, then you would release more gravitational potential energy. It's exactly the same here. Greater height electrical potential, you're going to release more energy. greater amount of charge, then you're going to release more energy. So that's where this equation comes from, that idea. This is the power dissipated rather than the energy dissipated. If you remember, again, back to 211, so power is the rate that energy is transferred. So it's the amount of energy that, say, got released in the electrical circuit divided by the time over which it was released in the electrical circuit. Yeah?
Why is there more positive on the right side?
Oh, there's no, that's just, it's just called artistic license. Okay. There isn't, right? So, you know, somebody has drawn, not me, so I'm blaming. That's what I mean, I always do. You know, they just drew five charges, right? There are actually 10 to the 28 charges in this section of wire, so I guess they didn't draw them all. So that has no meaning that there's 3 over here and 2 over here. That's a good point. Let's not get confused about that. So that is a good point. Where was I going? So power is the rate of transfer of energy. So all I've got to do is divide this loss of electrical potential energy divided by the elapsed time. And if I divide Q times delta V by the elapsed time, I'm going to get charge over time. That's the current. And so the equation for the power is just current times the voltage difference, potential difference, rather than the charge times the potential difference. So think of just the Q delta V and the I delta V for the electrical energy dissipated, the electrical power dissipated. Those are the 2 important equations here. So let's look at an example problem involving power and energy so we can work with these equations. So in this particular problem, I'm asking you to imagine a flashlight. And we're told that this flashlight is carrying a current, when it's on, of 0.1 amps, so 100 milliamps, and it's on for 12 hours. And it's carrying that current. That current is delivered by a 1.5 half-volt battery. So we're told that information. Now, with flashlights, what I always do, I put them on, I just need them for a moment, and then I just leave them on. And so every time I go back to them, the batteries run out. And it's because it's consumed a lot of energy. We're going to see that. So we've left our flashlight on, unfortunately, for 12 hours. And we're going to calculate how much energy is consumed, how much power is delivered. We're going to calculate how much charge went around the circuit involving the flashlight. How many electrons, that's interesting, how many electrons went around the circuit? We'll figure out all of these things. Okay, I'll do this on the document camera. Okay, so here's my question. And I started working on it by drawing the diagram for the circuit of the flashlight. So the flashlight, like all the circuits we met today, like that very first circuit of a little incandescent light and a battery, is just this simple circuit where we've got a battery and we've got a resistor, and the resistor's connected to the battery with 2 wires to the 2 terminals of the battery. So that's the circuit that describes the flashlight. We're told some information, so I wrote down that information. We were told that the current flowing in the circuit was 0.1 amp, and we're told that the battery supplied a voltage to the circuit that's 1.5 volts. And so here's my 1.5 volts, here's my 0.1 amps. The other thing that we were told is that the battery, the flashlight was on for 12 hours. And so 12 hours is that 43,200 seconds. That's where I got that from. And then we're going to work through the various questions that were asked in this problem. We were going to figure out the power that the battery is delivering to the circuit. We're going to figure out the energy that gets delivered to the circuit over 12 hours. We're going to figure out the current, the charge that flowed around the circuit. And we're going to figure out the number of electrons that flowed around the circuit. To get an idea for all these sort of numbers, by calculating these numbers, we can get a picture, an idea, a more concrete picture idea of what's going on in this sort of average, everyday electrical circuit that we've all met. Okay. First question then is power. P for power. And power dissipated in a resistor. And so that's also the power that's delivered by the battery is equal to, we just met this equation, the current that's flowing times the voltage difference. So think about that resistor. That resistor, from perspective of energy, is dissipating electrical energy. That resistor is providing a resistance, pebbles and rocks, ions, to the flow of the current. So it's dissipating electrical energy. And that rate of dissipation of that energy, those joules per second, those watts, is the current times the voltage difference, the potential difference across the resistor. The current in this particular case is 0.1 amps. The voltage difference in this case is 1.5 volts. And so 0.1 times 1.5, that's 0.15 watts, or that's, joules per second. And so that's the rate that the flashlight is dissipating power. It's just 0.15 watts. What's the total energy that got dissipated? So I'm going to call that delta PE. That total energy dissipated, well, let's just think of the definition of power. Power is the rate of dissipation of energy. So if I multiply the power, P, by the time interval, T, that's going to take the joules per second of power into joules, just a total amount of energy dissipated. And so if I multiply, I've got 43,200 seconds. I've got 0.15 watts, or 0.15 joules per second. If I multiply those two numbers, I got 6,480. That's joules. So that's the joules of energy that get dissipated over the 12 hours. So, from the perspective of energy, 0.1 watt, that's a rate of energy dissipation that's not very large, right? But because it was dissipating for 12 hours, a lot of seconds, it was a lot of joules of energy we wasted by leaving the flashlight on. So it was a big waste of energy, more than 6,000 joules. Next question was, we've done the energy. We want to find out how much charge ran around the circuit in that length of time. Well, here we can use our definition of electrical current. The electrical current in a circuit is the amount of charge that flows through the... Yeah. Oh, sorry. Thank you. It is already unclear, but that would make it really unclear. The electrical current that's flowing in the circuit is the amount of charge that flows divided by the time interval over which it flows. That's the definition of electrical current. It's nothing other than that. We want how much charge flowed. So we can find the delta Q. simply by multiplying the current, which we know, by the time interval, which we also know. All we've got to do is multiply the 0.1 amps of current by the 43,200 seconds. So when I did that calculation, I got 4,320, and that's coulombs. That's an amount of charge. So that's the amount of charge that flowed. That's a lot of charge. If you think about when we were talking about, we spent a long time on charging things by rubbing things. And we said that when we charge things by rubbing things, if I rub the glass rod with the cat's fur or the plastic rod with the nylon, I can get, nanocoulombs and microcoulombs of charge on those things. But in this case, what you're seeing is there's a massive amount of charge that was pushed around the circuit by the battery. It was thousands of coulombs per charge. If we want to calculate the number of electrons, how am I going to calculate that? This is the last step. The amount of charge that got pushed around, it was delta Q, I called it, is the charge on each electron multiplied by the number of electrons that were pushed around the circuit. I'm going to call n that number of electrons. So this is just simply the idea that the charge that flowed around the circuit comes in little packets. Each little electron has a given amount of charge, 1.6 times 10 to the minus 19 coulombs of charge. And so if I get a certain total charge, I can figure out the number of electrons n that corresponded to that total charge. All I've got to do is divide delta Q by E. So this is this large number of 4,300 coulombs divided by the tiny, tiny, tiny number of minus 1.6 times 10 to the minus 19 coulombs. It's 2.7 times 10 to the 22. And that's just a number. It's unitless. It's a number of electrons. So a massive number of electrons walk around the circuit.